All right, so we have one more example pertaining to banked curves that we're going to talk about. So we have a car's tires have a coefficient of friction of mu sub s with the road. Suppose you're given the banking angle to be some theta, where theta is greater than arctan of mu sub s. So the car would slide down if its speed is 0 and the radius of curvature is r. Find the minimum and maximum speed that the car can travel without slipping on the road. So in this case, there's two cases we need to consider. The first case is to find some minimum velocity. So taking the example when, let's say, the car is sitting here at rest. If the car is sitting at rest, since the critical angle is greater than arctan of mu sub s, this car would actually start slipping down the banked road if it's sitting there at rest. So it needs some minimum velocity to keep moving through the curve to keep contact with the road. And then on the other hand, if the car drives too fast through the banked curve, it would skid out. And in that case, we have the force of static friction between the tires and the car acting in this direction, keeping it from skidding out as we approach this max velocity. So let's consider this first case of calculating V minimum, and then a very similar calculation can be done for V maximum. So to do the V min calculation, we have our free body diagram like we did in the previous slide, and we're taking the XY coordinate system to be horizontal and vertical because the centripetal acceleration is solely in the horizontal direction, so we want to make use of that. So the normal force makes an angle of theta with the vertical axis, and then the force of static friction makes an angle of theta with the horizontal axis. So we can calculate each of the components. All right, so doing the sum of the forces in the x direction, first we have the x component of the normal force, which is n sine theta in the positive direction, and then we have the x component of the force of static friction. So in this rectangle, that would be the adjacent side. So we have minus fs max cosine theta, and those are the only two forces acting in the x direction. And that is equal to mv squared over r. Basically, this is the expression for mass times the centripetal acceleration. All right, then and note that we're assuming that we're maxing out friction in this case to get that minimum speed. So if we max out our static friction, we can plug in the expression that maximum force of static friction is mu sub s times n. So we have an equation here in terms of the velocity and the normal force. Now to get the normal force, we're going to do the sum of the forces in the y direction. In the y direction, we have force of gravity acting downward. So that's this middle term. And then we have the y component of the normal force, which is n cosine theta, and the y component of the force of static friction, which is fs max sine theta. And again, here for the max static friction, we've plugged in mu sub s times n. So if you algebraically rearrange this equation and solve for the normal force, we get the normal force is mg divided by cosine theta plus mu sine theta. Then we're basically plugging this expression in for the normal force here and solving for our velocity. So after we rearrange our sum of the forces in the x, we basically get that the velocity, the minimum velocity, is equal to the square root of this expression. And you can take a look at the limiting case where we let the coefficient of static friction go to 0, and you should see that you get the same result for the velocity as you would have when you did the calculation for the critical angle theta that needs to be there so that you don't need friction. So go ahead and compare this answer to the homework problem you did that requires you to calculate that critical angle. All right, and then for calculating the Vmax, you will go through a very similar set of steps, except now you have the force of static friction acting down the ramp, keeping you from skidding out. In that case, your x component is going to be a sum of the x component of the normal force and the force of static friction, providing you with mv squared over r. And in the y direction, you have the normal force in the positive side, and then you have the y component of force of static friction and force of gravity. And doing a similar set of steps in the algebra, you can calculate Vmax for this case.